Okay, so the next speaker for the day is Indrakshi Raychowdhury from the ICTS Pilani and the Goa campus. And she's going to talk about Loop-String-Hadron framework for SU3 lattice gauge theory. Go ahead.
Okay, thank you very much for giving me the opportunity, especially speaking in this hybrid mode. So I'll be talking about a very recent development that is important towards the goal of quantum simulating QCD. So as all of us are fairly aware that currently we are witnessing a change of paradigm where we are moving from the classical computation era to the quantum computation era. And as physicists at this point, our role is kind of identifying the physics problem that would actually benefit from quantum computation and then work accordingly, like towards building quantum algorithm, NISQ and beyond and so on. So as lattice gauge theorists have already found that this quantum computing maybe is hopefully will be really useful to solve certain unsolved regime of lattice QCD problems, such as doing computation without sign problem, dealing with real-time dynamics and all. However, the lattice gauge theory calculations in these two computation regime are actually different, because they are kind of orthogonal directions. They require different theoretical frameworks naturally, and they also look for different research directions or different objectives. And the computational methods are also entirely different. So as I mentioned, the goal of a significant part of the lattice QCD community has become to work towards performing lattice QCD calculations using a quantum computer. But to start with, this is too complicated. So what people have already started doing is to look at simpler yet similar models. Such examples that have been explored quite widely is, let's say, the Schwinger model, which is an abelian gauge theory, the QED in some lower dimension. And there also has been popular models such as quantum link models. I think yesterday's talk, Schaich has discussed this aspect as well. There have also been interest in dealing simpler gauge theories with discrete gauge groups, or even non-abelian gauge theories, which are with some simpler gauge groups such as SU2. And this has also led to some emergent research directions towards developing analog quantum simulation protocols, developing digital algorithms, performing tensor network calculations that is actually doable with classical computers, and of course working towards hybrid algorithms for combining all of this. So if we look at the state of the art of this emergent research direction, you will find that there are lots of works that are coming up, and more groups are being engaged in this direction. This is not at all an extensive list of references, just give a hint that what is happening in this field. However, in practice, if you look at what has actually been happened towards finally dealing with the QCD, which is the SU3 gauge theory, you will see that that list of reference is pretty limited. There has only been 3 works reported in this direction, and those 3 works are also very limited. For example, for a small dimension or very small lattice, or only with very specific boundary conditions, something like that. So the thing is that we have seen very limited progress in context of SU3 gauge theory, and this is also true for any non-abelian gauge theory. The list that I have shown you in the previous page, here you will see some papers with the title SU2 or SU1, but those list of references are more or less close to being exhaustive. Whereas there are hundreds of more papers with Schwinger models or abelian gauge theory. So the summary is that the progress with non-abelian gauge group has been limited. And if you look at the real experimental demonstration for quantum simulation that has been obtained so far, there has been quite a few significant developments in recent years. But The fact is that till date, all of these still deal with abelian gauge theories. And so the question is, how can one make non-abelian gauge theories accessible on a quantum computer? So towards that question, one must first will have to look for what is the natural framework for quantum simulation. Unlike the conventional lattice-QCD approach, that is the standard framework that is most suitable for quantum computing is Hamiltonian framework that has already been developed by Kogut and Susskind back in 1975, and this comes naturally. So let's have a very quick look into the Hamiltonian framework, although I'm sure that many of you are already aware of this. So the Hamiltonian is for gauge theories that are obtained by a temporal gauge fixing that leaves the time continuous and the lattice, the space becomes discretized in a lattice. The canonical conjugate variables of the theory are the electric fields and the link operator that satisfy the canonical commutation relations. There is a Hamiltonian containing different terms. There is an electric term, a mass term, fermionic mass term, a matter gauge interaction term, and a magnetic term. The extra thing that you have in a Hamiltonian formulation is the Gauss law constraint. That is a constraint that is true for all lattice sites in. The physical Hilbert space is annihilated by the Gauss law constraint, and the Hamiltonian commutes with the Gauss law constraint. So quantum simulating or simulating Hamiltonian dynamics of a gauge theory requires imposition of this Gauss law constraint. That is some non-trivial job. Now, what is this on-site Gauss law constraint? Roughly, this on-site Gauss law constraint deals with the imbalance between incoming and outgoing electric flux to be balanced by the matter content of the theory. Now, as I mentioned that you have seen, we have observed so much of progress with abelian gauge theory, unlike non-abelian. Why is it so? If you look at the abelian gauge theory, such as with gauge group E1, there the link operator holonomy is just a phase. And the Schwinger model that one mostly interested in, that is in 1 plus 1 dimensional. So there this placket term doesn't exist. So the magnetic term from the Hamiltonian drops. The Hamiltonian becomes pretty simple. However, when you go to non-abelian gauge theory, the Gauss law constraints contains the color index. And that denotes a number of mutually non-commuting constraints to be present simultaneously at each lattice site, and that needs to be satisfied by the physical Hilbert space. And as you go to the gauge group SU3, the number of such constraints increase, becomes from 3 to 8, but still the philosophy remains same. So that is the major obstacle that one faces while dealing with non-abelian gauge theories in context of quantum simulation. So that is why there has been some recent and renewed interest in Hamiltonian framework as well. And there has been several attempts to find some reformulations of the original theory so that it becomes possible to compute, to do some explicit quantum computation or quantum simulation for that model or the system. So recently we have performed a thorough search to find one efficient formal formulation that might have some benefit over the others towards the goal of quantum simulating non-abelian gauge theories. And we have actually started from the Kogut-Susskind Hamiltonian and looked at several different basis choice or reformulation of the same that has been achieved recently and is also being used by several groups. However, the analysis that we have performed, we have found that one particular framework is kind of preferred. If you look at the computational cost, this red line shows the computational cost for this Loop-String-Hadron framework for a Hamiltonian simulation. So what is this Loop-String-Hadron framework? This is a reformulation of the original Kogut-Susskind Hamiltonian where the Hamiltonian dynamics can be described. What is the why is it beneficial or why is it advantageous to work with that? Because in this framework, there is no need to impose the Gauss law constraint. That actually leads to a significant reduction in the computation cost. So let's have so in this talk, I will give you a brief overview of what this Loop-String-Hadron Hamiltonian is and our recent results of obtaining a Loop-String-Hadron formulation for SU3 gauge theories. Okay, so here you can see in this figure that this Loop-String-Hadron Hamiltonian is actually obtained from Toby-sustained Hamiltonian via the path of prepotential framework. So the prepotential framework of gauge theories is a set of work that has been started by Manu Mathur in 2005. I did my PhD in this topic, and thereafter also the work has continued, which has been a series of developments to provide this framework for even for arbitrary SUN gauge group that has several benefits that I will come close slowly. Now, recently, with another collaborator who was a grad student then at IMT, I combined this prepotential framework with staggered fermions to obtain the Loop-String-Hadron formulation for SU2 gauge theory. So let's quickly have a look at what prepotential framework is. As I mentioned, the canonical conjugate variables of any Hamiltonian framework are the electric field, left and right electric field, and the link operator. In the prepotential framework, those original variables are replaced by a set of harmonic oscillators. This is the example for SU2 gauge theory, so that corresponds to a harmonic oscillator doublet associated to left end of a link and right end of a link. And as a result of this construction, where this electric field is constructed out of this left and right oscillators, and surprisingly, this link operator, which is a SU2 valued matrix operator, SU2 group valued matrix, so that is also constructed in terms of these oscillators. And surprising fact is that this link operator actually breaks into two parts, one left part, one right part. The left part is constructed only out of left oscillators, and the right part is constructed only out of right oscillators. So earlier variables, what was non-local connecting these two links, this is now kind of breaks into two local parts that those are associated with both ends of the link. Now, what remains non-local? In this formulation, still there remains something non-local, that is a constraint which connects that this total number of oscillators at the left end must be equal to the total number of oscillators at right end of the link. So this is an extra constraint that appear in this formalism that is called, that we call as abelian Gauss law constraint, and this basically connects the on-site content of oscillators at this side to this side. Now, what happens when we include staggered fermion to this formulation? So let's look at this picture. This is a one-dimensional lattice where you have a site that can contain matter fields. You have a fermionic doublet here. And towards this end, you have a set of oscillators. Towards this end, you have a set of oscillators. So now you have a set of local ingredients. All of them transform in the same way under the group SU2. So what you can do, you can form local SU2 invariant objects out of these ingredients. There you can form some objects, those are purely bosonic, that you create out of these bosons and these bosons. Like this, we call these as local loop operators, as they are purely bosonic. You can construct something like combining bosons and fermions. Those are like corresponds to some string end operators, and similarly say boson at this side and fermion, or boson at this side and fermion can form another set of operator, and of course you can form purely fermionic singlet as well. Explicitly, those operators are written something like that. You don't need to pay attention in the detail, but these are these objects. So what happens? So now one can actually define a local or on-site Hilbert space that is completely SU2 invariant, where the states are being created by these local singlet operators that I have shown in the previous slide. So this is, for example, this operator, this operator, this operator, they create a Hilbert space. And those states can be characterized by a set of integers, among which one integer corresponds to the counts the excitation of the pure gluonic flux. So that integer can take any values, any integer values between 0 to infinity. And these two have some fermionic content, so they can take only values between 0 and 1. So what are these? These are, if you imagine what are the gauge invariant states or gauge invariant configurations that you can have on a lattice. Those are basically Wilson loops or strings or hadrons. Now, if you just concentrate on one particular site and take local snapshots at each possible site, what can you see? For one dimension, you can either see flux flowing across that site, or you can see a flux ending at the site, or you can even see a flux originating from that site. So these are the three excitations, local excitation, those are being characterized by the local Loop-String-Hadron quantum numbers. And what is missing? The missing is the weaving along the link, because you have the on-site pictures. To relate it to a valid global configurations, they need to be waved along each of the links of the lattice. And this is actually done by the abelian Gauss law constraint that connects that these total number of flux lines should continue until the next site. So if you look at this as a sample configuration, this number of lines must equal to these many lines coming here. So this is basically the statement of the abelian Gauss law that guarantees the continuity of electric fluxes across any of the links. So as I mentioned, the Loop-String-Hadron formulation has two key ingredients. One is local gauge invariant Hilbert space and local constraints on each link. Those are the abelian Gauss laws. So now our aim is to find a similar formalism for SU3 gauge theory such that we can access QCD in a better or accessible way. Okay, so as the first attempt, I have shown the example of SU2 gauge theory in 1+1 dimension so far. What if we consider SU3 gauge theory, and what we need are the basic two ingredients of the Loop-String-Hadron formulation. The starting point of that is again the prepotential formulation for SU3 gauge theory, and it actually exists in the literature. So during my PhD works, I have found with my supervisor Manu Mathur and Ramesh Anishetty, I have found a way to obtain the prepotential formulation for SU3 gauge theory, although that is not very straightforward generalization of SU2, because the SU3 being a rank 2 group requires a fundamental as well as an anti-fundamental representation or two species of Schwinger boson triplets as the fundamental ingredients. And being defined on the same position or the same link, they can form a singlet, and that gives rise to a multiplicity problem for SU3 Schwinger boson representation. However, we have obtained a solution for this multiplicity problem in terms of variables called irreducible Schwinger bosons. And these irreducible Schwinger bosons are pretty similar to the SU2 Schwinger bosons, or they create the irreps of SU3 directly. One no longer needs to symmetrize or antisymmetrize these objects to get an SU3 irrep. So this has led to the prepotential formulation for SU3 gauge theory. So if you now look at the ingredients, as I have mentioned earlier, the original variables were left electric field, right electric field, and the link operator. Now, instead of that, you have a pair of Schwinger boson triplet and anti-triplet, 3 and 3-star representations. And they are defined on the same end of the link, one set for the left end, another set for the right end for each of the links. So in terms of these variables, one can reconstruct this original canonical conjugate variables and yet obtain the result that this U actually breaks into a left part and a right part. So this construction is very much similar to the SU2 prepotential construction, except the fact that these bosons are not ordinary Schwinger bosons, but some involved mathematical construction, those we call as irreducible Schwinger bosons. Now, as I earlier mentioned that the prepotential formulation comes with an abelian Gauss-Law constraint. For SU3 case, there are actually two abelian Gauss-Law constraints. One, and those actually imposes the continuity of the flux lines across the link. Now for SU3, the flux lines are directed. They always flow from triplet to anti-triplet. So there can be two directions of the flux lines. One is along this direction, another is along this direction. Those two are imposed by these two Gauss-Law constraints. So this was the prepotential formulation for SU3 gauge theory. Now as we include matter to it, the picture remains very similar to what we had for the SU2 case. Just the difference is that here you have more species of bosons. You have one triplet, one anti-triplet, same for the other side of the link as well. So if you look at the local ingredients that you can have in general, this is a list of the ingredients, but still you can form singlets either by taking a symmetric combination of them or by taking an antisymmetric combination of them. So you can exhaust the list of forming the singlets. In the same way, that leads to a finite set of fundamental creation, but SU3 invariant operators that can be defined at one side. For example, these are the purely bosonic operator that has been created by contracting this triplet and anti-triplet with deltas. And similar, these ones contains some antisymmetric combination of one psi and one fermionic and two bosonic, or two fermionic, one bosonic, or even three fermionic degrees of freedom. So this is how you obtain a fundamental set of SU3 invariant creation operator. So now we want to define a local Hilbert space that will be characterized by some quantum numbers that would correspond to this set of fundamental local loop string operators. So we do it in this way. So the state that we construct is characterized by 5 quantum numbers. Let's look at what are these quantum numbers. Okay, here is some pictorial representation. Now this A dagger I dot B dagger O, this is a purely bosonic operator, and that shows a flux flowing along this direction, along the orange lines, arrow with arrow. And the other purely bosonic operator shows the flux along this direction. So we can see that these two are the bosonic bosonic quantum numbers that can range from 0 to infinity for a gauge theory. The fermion and boson combined way, we assign it to 3 fermion boson but gauge invariant quantum numbers. Let's say these are 3 fermionic excitations present at this site. Either of these can be 0 or 1. But whenever this is 1, to make it a gauge invariant, this always comes with one flux going out of this along this direction. Similarly, when this new I index becomes 1, it is associated with a flux going out. Similarly, these two can appear simultaneously as well. However, if this middle one and outgoing one, these two are 1, that corresponds to a flux actually coming into this system, into the site. And similarly here, having the input 1 and middle 1 corresponds to a flux, incoming flux to the site from these particular directions. So we can categorize all possible combinations of being a fermion present on that site in a gauge invariant way by putting some 0 and 1 values corresponding to these 3 fermionic excitations. Now, one important thing is note that if you go back to the earlier picture here, we have a 3-component fermion present. It already has 3 components. But note that the excitations that we describe here, these are not really the 3 occupations number for all these 3 components. It's not. It's a particular gauge invariant combination that has all the components of psi, contributions from all the components of the fermionic fields, and as well as the outgoing bosonic field. So these are kind of the string end operators that we have. And of course, you can have hadrons as well, that is represented by all these 3 fermionic quantum numbers being 1. Again, just like the SU2 case, all of these configurations are nothing but snapshots of a general Loop-String-Hadron configuration that can be present for each lattice site. And one would further need to weave these along the links because you have local representation independent of each other at each of your lattice site. And there comes the abelian Gauss laws, here actually 2 of them to play the role. Okay, so in summary, we have a local SU3 invariant states characterized by the 5 quantum numbers. 2 of them are bosonic and 3 of them are fermionic. The set of these quantum numbers at neighboring sites are not independent. So the whole Hilbert space, the global Hilbert space, is not really a tensor product Hilbert space, but they are constrained by this kind of on link constraint. There are 2 of them, and this constraint basically relate all the quantum numbers at site, say R, to all other quantum numbers at site R plus 1. This is the algebraic description of the abelian Gauss law constraint. So this forms the key ingredients of the Loop-String-Hadron framework for SU3 in 1 plus 1 dimension. Now that's not enough. We'll have to find a representation of the Hamiltonian in this basis. So we proceed in that direction. I have already shown you that in the prepotential formulation, the canonical conjugate variables are re-expressed in terms of fermion, in terms of bosons, the Schwinger bosons or the prepotentials. This results that the Hamiltonian becomes actually Hamiltonian contains some local on-site building blocks. Those are the on-site SU3 singlets operators constructed out of bosons, fermions, or purely fermions, anything, in all possible ways. So these are the set of operators, those act as the local building blocks for the Kohut-sustained Hamiltonian when you rewrite everything in terms of prepotentials coupled to staggered matter. So now what we want to see, the action of these operators on the Loop-String-Hadron basis that we have defined locally. One important observation is that these operators basically change these quantum numbers by plus minus 1 unit or some other complicated combination of them. But the fundamental action is these quantum numbers are changed by plus minus 1 and follows the same statistics, like these 2 being bosonic and these 3 being fermionic. So we can formalize this in the way we can define a set of number operator that corresponds to the occupation number for the Loop-String-Hadron quantum numbers, and also a set of normalized ladder operators that corresponds to change in this Loop-String-Hadron quantum numbers by plus minus 1 unit in such a way that any particular state is defined to be created by this set of ladder operators acting on the purely vacuum state, that it's a 0 state. Now one can write the Kohut-sustained Hamiltonian in the Loop-String-Hadron basis. That is actually in terms of the Loop-String-Hadron operator. By Loop-String-Hadron operator, I mean this set of operators, this set of number operators, and this set of ladder operators. So I will not put you too much detail here, but this is the exact Hamiltonian. The Hamiltonian looks this. The electric Hamiltonian is diagonal, that is consisting only of the number operator in this Loop-String-Hadron basis. The fermionic mass Hamiltonian is purely in terms of fermionic number operators in this basis. And the matter-gauge interaction term contains the ladder operators. If you look here, this is a set of ladder operator that is defined at site R, and these are another set of ladder operators that is defined at site R plus 1. And there are combination of them do appear, where you can see the ladder operators corresponding to O, I, and M. Those are the three fermionic degrees of freedom, nu I, nu M, nu O, that I mentioned earlier. Now, this Hamiltonian looks complicated, I agree, but the important fact is that this SU3 Hamiltonian that we obtain in a very complicated way and through a lot of mathematical details, ultimately the final result looks, the structure is identical to the structure that we had for SU2 construction. And we have also numerically benchmarked this SU3 Hamiltonian against a pure gauge choice Hamiltonian, where one gets a purely fermionic theory with long range interaction that describes the same theory, the same spectrum. So I will not go into detail of the purely fermionic formalism that one can obtain by gauge rotating the fermions and also gauge rotating the link operator in this way, so such that your Hilbert space becomes purely fermionic Hilbert space with 3 fermions present at each site. However, the important thing to note is that the Loop-String-Hadron computation leads to a basis that is still cheap than the purely fermionic bosons, even with the maximum possible cutoff for open boundary condition. This is because this fermionic formulation contains some degeneracy that is completely absent in the Loop-String-Hadron. Okay, so I think our time is almost over, so I'll very quickly go through some of the application. Another thing is that why would one consider Loop-String-Hadron framework? The thing is that for SU2 gauge theory, we have seen several important applications of the LSH framework in context of quantum simulation. I'd like to mention a few of them. The very recent one is we have been able to find a symmetry protection protocol for SU2 Loop-String-Hadron. And this is a very recent work, and this is done with my grad student, Emil. Emil is actually in person present in the conference, so he may be able to talk to you regarding this later. The important finding here is that in this work, we have prescribed a protection scheme for the global symmetries of the theory that is also feasible for experimental demonstration as well. And this magic of this construction is that this protection of global symmetries immediately imply complete protection of all the local symmetries for the theory. So as a result, one can now quantum simulate a non-abelian gauge theory without imposing any local symmetry. Of course, one can understand that imposing global symmetries are much easier from practical point of view, whereas imposing local symmetries are horrible, specifically for non-abelian case, it's most impossible thing to do. And this is also very much important in context of tensor network calculations, because imposing global symmetries for tensor networks are also comes naturally, whereas the local symmetry doesn't act that way. Okay, also I will not go into detail, but the Loop-String-Hadron for SU2 has been useful in context of proposing actually realizable or immediately realizable analog simulation protocol as well, as explained in this research, in this recent work that comes with a very minimal error. And also it has been useful in context of analog, in context of digital quantum simulation. Sorry, this slide stays long. And this is one result is present in the literature, and more results are coming up by the group at UMD. And there are many other works that is currently going on regarding the Loop-String-Hadron for SO2, regarding tensor network calculations, and also understanding the entanglement structure for non-abelian gauge theories. Okay, so as I mentioned, this recently reported that I have just explained to you that Loop-String-Hadron for SU3 is structurally identical to the SU2 construction. So we expect to see the advantages that we have seen for SU2 to SU3 as well. However, the actual job is to find a Loop-String-Hadron framework for 3+1 SU3 gauge theory, and that would be no doubt a concrete step towards quantum simulating full QCD. Okay, I'd like to thank all of my collaborators, all of the hosting institutes and the funding agency, and of course all of you for listening.
Thank you very much. Okay, we have some time for some questions. Richard.
I think it worked. Yeah. Hi. Thanks for a very interesting talk. As I understand, your choice for the quantum link is a bilinear bosonic operators, correct?
Yeah.
Yeah. I mean, there are many. Look at the basic algebra of quantum links is exactly the algebra you have, but of course, given an algebra, there are many realizations, and you're exploring a whole avenue, and that's good. We should explore more and more because they may have different advantages. But if you decide to make the quantum links out of fermions, then you don't have any infinite Hilbert space at all. And everything goes through exactly as you say. Gauge invariance means that all the Hamiltonian is always the dot product between triplets or whatever group you're in of pairs of fermions. So the entire thing is actually a bosonic system. And you can show that gauge invariance is automatic. You can show that all the bosonic systems can be turned into qubits. This is a generic property of quantum links. And as far as I understand, but I'd really have to look at what you do more carefully. I'd love to do that. Why don't you email me and we can discuss it. But I think that's a general property that you're finding in your realization, and that it would actually be true of the entire quantum link formulation, which is this is, I think, an instance of. And but anyway, as I say, I can't understand what you said so quickly, so I may be wrong. You should always be aware of that. But I believe this is actually within that category. The gauge invariance, the Gauss's law commutes with a Hamiltonian. That means you don't have it as a constraint. As soon as that's true, it's no longer a constraint. A constraint is something you have to do to push yourself into a Hilbert space. But as soon as it commutes with the Hamiltonian, then of course you never get out of that space. So there is no Gauss's law constraint.
So
Okay.
here is the thing is that this, if when you define the variables, let's say the original variables.
Yeah, as I say, that's a property of the
terms
entire system. As soon as you write it this way, you get that property.
Yeah.
No matter
So
what your
here
realization is.
Here you don't have gauge invariance inbuilt.
Excuse me?
Gauge invariance, the Gauss law constraint is still not satisfied here. These are the variables, just that it already contains the color index. You will have to construct the color singlet operators or color singlet basis to.
What I'm saying, as soon as everything is a dot product between a triplet and an anti-triplet throughout the whole thing, which is true in general, then you can't get out of that sector.
Yes, of course, you can.
Right, so that's true of any representation of the quantum link problem.
But this will be the abelian Gauss law constraint holds, unlike the
No, that's also automatic. There's no constraint. I mean, you can stay in that sector. It's a super selection sector. Well, anyway, we should discuss this, but
yes.
To be honest, I have to look at your paper to really understand it in detail, and it's very, very interesting. So,
thank you so much.
But please, if you want, get in communication, and maybe I'll understand what you're doing better if you do that. Sounds good.
Okay.
Thank you very much.
I think we should thank the speaker again.